So now we're going to look at some basic GIS concepts. So GIS, well, it stands for Geographic Information System. GIS data have a spatial component, so they're aligned to the Earth's surface via some coordinate system. So GIS provides a tool for establishing the spatial relationships between data. It allows you to answer spatial questions, such as how close is my house to an active fault? As a geologist, that might be important to me. What is the maximum slope of the proposed road that I'm building going to traverse? As an engineer, that's important. If I'm away on a business trip, how many bars are there within 500 meters of my hotel room? Or as a homeowner, again, is Ruapehu visible from my property?
So a GIS can display data, and that data can be vector or raster. Vector data stores spatial information as either points, lines or polygons. So for a point it stores an X and a Y coordinate, for a line it stores an X and a Y at the beginning and end and at each vertice along the line, and for a polygon it stores that information for every vertice around the perimeter of the polygon. The GIS can also store attributes about each of those features, i.e. a point, line or polygon. So in the table at the bottom of the slide you can see geological data where we've got information concerning the name of the geological unit, its description and other information stored on the polygon. The other form of data a GIS can use is raster data. Raster data records spatial information in a grid of square cells, generally equal sized, and these are organised in rows and columns. Each cell stores a numeric value, and that value could be related to a geographic attribute such as the elevation above sea level, or as we're more used to in raster data, a colour, a JPEG. So when you look at your photograph, basically it's giving you a value that relates to the colour. In the images at the bottom of the slide we can see 4 raster data sets. On the left is an elevation data set, green around Wellington Harbour. The green shows the harbour area and red shows the higher hills. On the right is just a raster image from an aerial satellite. That's how we're more used to seeing raster data. And beside the satellite image is a hillshade. So this is an elevation model but converted with illumination to give us a more normal view of elevation data. When you add spatial data to a GIS, you're not storing the data in the GIS. When you put data in Excel, it's actually in the project. In GIS, you're just adding a pointer to the data. The data remains somewhere else, and all you're doing is saying, this is where the data is, and this is how I want to see the data displayed. The same data can be used in multiple projects, or it can be used in the same project multiple times, but it's just viewed in a different way. Removing the data from the project does not delete the data, but you have to remember that if you edit the data, changes will be permanent, and every other project that views that data will see the changed data. Now we're going to look at projections, something quite important in GIS. So GIS data, as I said, was stored in coordinates, and these may be a geographic coordinate system, generally referred to as a GCS, or a projected coordinate system, which is a PCS. So the basic differences between these coordinate systems are demonstrated in this diagram below. Geographic coordinate system is a reference system that describes positions on an ellipsoid, which is the representation of the Earth's surface. Geodetic datum is a series of numbers that define the shape and size of the ellipsoid and its orientation in space. Location is given in terms of latitude and longitude, and coordinates expressed in decimal degrees or degrees, minutes and seconds. So that's referring to the position of something on the globe. A projected coordinate system is a result of projecting the ellipsoid onto a flat two-dimensional surface through a complex mathematical process. The projected coordinate system shares the same datum as the geographic coordinate system that it's based on, but the coordinate systems are typically measured in meters or feet. Most of the maps we see are in a projected coordinate system. looking at projections and how they relate to New Zealand. Well, in New Zealand we define coordinates in latitude and longitude in terms of New Zealand Geodetic Datum 2000. And this datum is equivalent to WGS 84, so this is a geographic coordinate system. But prior to 1998, latitude and longitudes were specified in terms of the Geodetic Datum 1949. So why would you care? They both use latitude and longitude, so what's the problem? Well, because latitude and longitudes are always specified in terms of a datum, and those two datums are different, data stored in Geodetic Datum 1949 and Geodetic Datum 2000 will give a different latitude and longitude for the same position on the ground. So it makes it difficult when you're trying to merge two data sets with different datums. Now looking at the projected coordinate systems we use in New Zealand. Prior to 1998 we used New Zealand Map Grid, and that was based on the Geodetic Datum 1949. But currently we're using New Zealand Transverse Mercator, which is based on the Geodetic Datum of 2000. Because these two projections have different datums, moving data between them is not simple. And a transform is needed to convert the data, either between geodetic datums or between the two projected systems. And the GIS offers several transformations to allow you to project data, but you need to understand that the accuracy that can be achieved by these different methods is not necessarily the same. So this table just shows that there are three standard transformations between projections or between datums and the level of accuracy that can be achieved. It's not a big difference if you're not dealing with survey level accuracy, but you should at least be aware of those levels of accuracy. So what about projections in polar regions? Well, all map projections are compromises. Some preserve scale, some local shape, and some preserve angles. So you have to choose your projection carefully. You can see in this picture that in the polar areas, the land area is expanded as you go towards the pole. Be careful when choosing which projection you want to use and when you're moving data from one projection to another. I won't tell you which one to use because it will depend on what is important to you, whether scale or shape is important in the final map. So what we've covered in this session is what a GIS is, the types of data that it can display, and hopefully you've learned that the data is not part of the GIS project, but it sits outside of the project and is just referenced by the project. And we've looked at projections and some of the associated issues. In future sessions we'll look at how to download QGIS and install it, and we'll run through putting data into a QGIS project and symbolizing it.